2,000 years ago, in the middle of the Iranian desert, people were eating frozen desserts in summer. Not in the mountains. Not in caves. In cities where summer temperatures climb above 40 degrees Celsius. No electricity, no compressors, no refrigerants. Just geometry, clay, wind, and physics. This is the story of the Yakhchāl, the Persian ice house that made and stored ice in the desert long before modern refrigeration. Across Iran, especially near cities like Yazd and Kerman, you can still find massive dome structures rising from the desert floor. Thick mud brick walls, conical silhouettes, some over 10 meters tall. These are Yakhchāls. The word literally means ice pit, but that translation barely captures the engineering. The earliest versions date back to the Achaemenid period, around 400 BCE, and the system matured under later Persian dynasties. By the time of the Sassanids, it was fully refined. It was not just a storage room, it was a climate machine. At first, this sounds impossible. Deserts are hot. But deserts also have something else: extreme temperature swings. During winter nights, temperatures can drop below freezing, even if daytime heat returns quickly. The Persians exploited that difference. They built shallow reflecting pools on the north side of the Yakhchāl wall, carefully oriented to block daytime sun while exposing water to the night sky. When the sun set, heat radiated from the thin sheet of water into the open sky. With clear desert air and low humidity, radiative cooling intensified the temperature drop. Water froze. By dawn, workers harvested thin sheets of ice and stored them inside the insulated dome. Night after night, they repeated the process, layer upon layer, until the ice chamber was full. The Yakhchāl was not random. It was geometry working with physics. The structure had three core components. The dome. The conical shape reduced solar exposure during peak heat. The thick walls, sometimes up to 2 meters thick, were made from a special mortar called sarooj, a mixture of clay, sand, lime, ash, egg whites, and goat hair. It was waterproof. It was insulating. It was durable. The dome's mass absorbed heat slowly during the day and released it gradually at night, stabilizing internal temperatures. The subterranean pit. Most of the storage chambers sat below ground. Soil is a natural insulator. Below the desert surface, temperatures are significantly more stable than above. By storing ice underground, they shielded it from temperature spikes. The windcatcher system. Many Yakhchāls were paired with badgirs, windcatchers. These tall ventilation towers captured prevailing breezes and directed them downward into the chamber. As air moved through, it enhanced evaporative cooling and pushed hot air upward and out. Airflow. Thermal mass. Radiative cooling. All passive. No fuel required. Persian engineers also mastered underground water channels called qanats. Qanats tapped mountain aquifers and transported cool water across long distances underground, preventing evaporation in harsh climates. In some regions, qanat water fed the Yakhchāl pools directly. Cool groundwater. Radiative freezing at night. Insulated storage underground. This was not a single invention. It was an integrated cooling ecosystem. Ice harvested in winter could survive through the peak of summer. Stored properly inside the thick-walled dome, shielded from sunlight and ventilated carefully, the ice mass melted slowly, often lasting until the next winter harvest cycle. In cities like Yazd, ice was used for preserving food, cooling drinking water, making early forms of frozen desserts, serving chilled syrups. Cold was not a luxury for the elite. It was infrastructure. The Yakhchāl worked because it respected three fundamental principles. 1. Separate heat from Massachusetts. The ice was isolated from direct sunlight and hot air. 2. Use the sky as a heat sink. At night, the desert sky acts like a thermal vacuum. Heat radiates upward into space. 3. Maximize thermal inertia. Thick walls delay heat transfer. The larger the thermal mass, the slower the temperature change. Modern refrigeration uses compressors and chemical phase changes. The Yakhchāls used sky radiation and clay. Different tools. Same physics. This system did more than store ice. It inspired passive cooling architecture across Persia. Windcatchers cooled homes. Courtyards created shade and airflow. Water channels evaporated and reduced air temperature. The Yakhchāls was part of a broader philosophy: work with climate. Don't fight it. To replicate a full Yakhchāl, you would need thick earthen or adobe walls, a shaded, north-facing freezing pool, a dry winter climate with freezing nights, subterranean insulation, controlled ventilation. In humid climates, radiative cooling is less effective. In mild winters, freezing may not occur reliably. But the core idea, thermal mass plus airflow plus radiation, remains powerful. Modern homesteaders use similar principles in root cellars and earth-sheltered storage. The ancient Persians simply optimized it for ice. When industrial refrigeration emerged in the 19th and 20th centuries, passive systems became obsolete in urban infrastructure. Electricity was scalable. Ice factories were profitable. Refrigerators were marketable. Passive climate architecture requires regional adaptation. It does not standardize easily across climates. It also does not generate recurring utility revenue. So it became historical curiosity instead of living practice. Yet today, as energy costs rise and grids become fragile, passive cooling is returning to architectural discussions. Not because it is nostalgic, because it is resilient. The Persian icehouse proves something critical: cold is not inherently technological. It is physical. We often assume comfort requires constant energy input. But for 2,000 years, desert civilizations maintained cold storage with geometry and clay. What else have we outsourced to machines that once relied on design? What other forms of infrastructure could operate passively? In an era of climate stress, rising power demand, and grid vulnerability, passive systems are not primitive. They are strategic. Imagine standing in the Iranian desert 1,500 years ago. The sun sets. The air cools. A shallow pool begins to freeze under a black sky. At dawn, workers lift sheets of ice and carry them into a clay dome that will guard them through the summer. It feels improbable, but it worked. For centuries. Not because of advanced materials, because of observation, because of iteration, because of alignment with climate instead of domination over it. The Persian icehouse was not magic. It was attention. And in many ways, that is the most powerful technology any civilization can recover. If you find these forgotten systems valuable, stay with this channel. There are thousands of years of quiet engineering waiting to be remembered.